Hello, what we're going to do in this video is we're going to look at the rattling ball experiment. This is what I was taught at school. It was called the rattling ball experiment, but it doesn't appear on YouTube or anything called the rattling ball experiment. But I'm going to stick with what I learned in school, and it's a question that comes up a few times, and there's a trick to solving this. The equipment we have is a signal generator connected to a vibration generator. That vibration generator is connected to a metal plate. Could be any material, but the metal plate does make it sound loud. And what we have on the top is we have a ball bearing. So the metal plate is set in oscillation, so it goes up and down. And what you do in this experiment is you increase the frequency or increase the amplitude of oscillations, and then there becomes a point where the ball starts rattling. It starts making this sort of rattling against the metal plate, and you can hear that. And what's happening there is the ball is losing contact with the plate and then regaining contact, so it's hitting against the metal plate, and that's causing the rattling. And the questions often ask about what frequency or what amplitude does this occur at, and it sounds quite a complicated question, and the reason I'm going through this is because there is a trick to solving this. So let's say we keep the frequency at 50 Hertz. When it moves a very, very small amplitude, if we pretend this pen lid is the ball and the pen is the plate, it moves up and down because the acceleration is low when it's moving a small distance in that amount of time. What happens then is if we increase the amplitude, what happens is the acceleration of the plate has got to increase because it's got to travel a greater distance in the same amount of time. The time period, the time for it to go up and down is the same. There then comes a point when the acceleration as it's moving down is greater than 9.81, greater than g. So what happens to the ball and the plate when the acceleration of the plate moving down is greater than 9.81? Pause the video, have a think, and restart when you're ready. So what happens when it's at low amplitude? The acceleration is always less than 9.81. So the ball is not falling faster. So the plate is not falling faster than the ball when they remain in contact. What happens when you increase the amplitude and the acceleration increases? is the plate has a greater acceleration than the ball. The ball will only accelerate at 9.81 because it's gravity that's pulling, or it's weight that's pulling it down, whereas the plate is being pulled down by the oscillator. So as it goes down, the plate accelerates faster and therefore travels a greater distance than the ball, and the ball loses contact. So that happens when the acceleration is equal to 9.81. What happens then is the plate then gets the bottom of its oscillation and then starts moving and then hits the ball, and that's what gives us our rattling sound. It moves up to the top, moves back down, loses contact. The ball carries on falling just under gravity, and then the plate comes back and hits it. So what we've got this periodic motion of the ball losing contact with the plate and then hitting it again. And what you can see here is you can see that this repeated motion is going to cause a sort of rattling, particularly if they're both made of metal. So we've got a question here. When oscillating at 50 Hertz, what is the maximum amplitude of oscillations that can take place without the ball losing contact? So we know that it's going to lose contact when acceleration equals g, which equals 9.81 meters per second squared. So we need an equation here to link the frequency and the amplitude. I'm going to go right back to the beginning equation for acceleration, a omega squared sine omega t. And what we want to know when the maximum acceleration during that cycle is, because we want to know when it gets 9.81, and that's going to be when it's the maximum amplitude. That's going to be when the acceleration has just reached 9.8. So what we want a max. And the only bit in here which changes, we've got the amplitude as a constant, omega is a constant, and we've got this that changes over time. So when we want to know what point of our cycle the acceleration is at its greatest, this is when sine is going to be equal to 1. So we can get rid of that, and we have A max equals A omega squared. I'm going to ignore the minus because that doesn't, the plus and minus doesn't really matter. I just want to know the angular frequency there. I think this equation is on the formula sheet, but being familiar with these fundamental equations does help you with simple harmonic motion. So we've got the frequency here, not omega, so I'm going to use omega equals 2 pi f. Make sure it is, it's not a great omega, but please make sure it is an omega, not a w. They are different. So a 2 pi f squared is equal to a 4 pi squared f squared. So we've got a fixed frequency here of 50 Hertz, so we want to know what the amplitude is. So A equals A max divided by 4 pi squared f, which is 9.81 divided by 4 times pi squared multiplied by 50 squared. I'll just type that into my calculator. 9.81 divided by 4 times pi squared multiplied by 50 squared is 9.9 times 10 to minus 5 meters, which is 2 millimeters. You can see that this plate would have to move a very, very small distance at 50 Hertz. 2015, that's the mains frequency there. So you'd hardly see this thing moving, and yet it would appear to rattle. So the key to these questions is this point here. When does it lose contact? Well, that's when the maximum acceleration is 9.81.